We are the Gujarat Technological University. Since its inception over a decade ago, GTU has been empowering young and curating minds to realize their true potential. Over 4 lakh inspired students are enrolled with one of the premier academic universities in India. With more than 450 affiliated colleges in its fold operating across 5 zones of the state, GTU, the International Innovative University, your place to move forward.
Okay, so good morning everybody. In earlier lecture we have discussed about amplitude shifting key, which is simply known as a ASK, where the informations are stored in form of an amplitude. If the input bit is 1, then the output of ASK modulator would be a cosine signal with the amplitude of square root 2 EB by TB. When the input bit is 0, the output of ASK modulator would be a 0. So here the informations are stored in form of a amplitude. Then we have discussed about the frequency shift key. So frequency shift key is simply known as a FSK. If the here the informations are stored in form of a frequency. If input bit is 1, then the output of FSK modulator would be a cosine signal with some frequency of F1. When the input bit would be a 0, then the output of FSK modulator would be a cosine signal with some different frequency F2. And in the same lecture we have discussed about the M FSK signal. Today we discuss the one other very important modulation scheme. It is known as a phase shift key. It is known as a PSK. So PSK is a one kind of modulation scheme where we can say frequency shift key is a one kind of a modulation scheme where the information is basically stored in form of a phase, in form of a phase. So that's why it is known as a phase shift key. The one of the very important application of phase shifting key is the CDMA system. In CDMA system is simply known as a code division multiple access system. In CDMA system, the key modulation scheme would be QPSK, and QPSK is a part of the phase shift key. So here the information is stored in form of a phase. We can have PSK with M is equal to 2. It's a MRE PSK. So if M is equal to 2, so we have only 2 input, 1 and 0. So it is known as a BPSK, binary phase shift key. If the value of M would be increased from 2 to 4 here, and then we have a quadrature phase shifting key because it have a 4 phase. So 4 phase is simply known as a quadrature phase shift key. So these two are the very important and very popular phase shifting key methods that we will take a look of this both in a in one lecture, and QPSK we will discuss in a next lecture. BPSK is binary phase shift key, and in this lecture we are going to discuss about the mathematical expression, how to represent the BPSK. Then we will see the graphical presentation. Then we will even learn about the constellation diagram of BPSK signal, the bandwidth requirement, the design of a transmitter and receiver for BPSK signal. Then we will learn about the MRE PSK signal, and very special case of MRE PSK signal is a QPSK, but we will try to address this part in the next lecture. So today's lecture we basically discuss about all these topics which is written over here. We will start first with the mathematical expression, how to represent the PSK signal. So as already mentioned here, the PSK signal is a signal in which the information of input has been stored in form of a phase. So if you imagine there would be a one PSK modulator and the input bit is a binary x of t signal which is in form of a 1010. So output of a BPSK modulator can be defined by this equation, that is square root 2 EB by TB cos omega ct plus theta I. This one is important. Theta I is the theta which is correspondence with ith symbol. So this I is represent the ith symbol. And if I would be vary from 1, 2, 3, so here the theta I can be represented as a 2 pi by n. So total phase here is 2 pi. Now if you start from here, so 0, and then here you can have a pi by 2, then here pi, then you have a 3 pi by 2, and then you have a 2 pi. So this all, the total phase is to be divided by the n points, where n is the number of symbol. If n is equal to 2, here it's a 2 pi by 2. If n is equal to 4, it's a 2 pi by 4, like this. So n defines the number of symbol or the number of constellation point. Now I is the variable. It's a simple integer, can be increased from 1 to up to, it will be goes to the nth symbol. So if there are n, so I can take the value up to the n. Now here we are learning the BPSK, binary phase shift key. So it has only two symbol. Input have only two possibilities, 0 and 1. So here the value of n would be 2. If you place this value, n is equal to 2 here, so this equation can be modified as 2 pi by 2 multiply with I minus 1, and I can vary from 1 to n. So if n is equal to 2, so I have only two possibility, 1 and 2. So theta I can have a two value. The first value of theta I is where I is equal to 1, so that is known as a theta 1. And the second value of theta I when I is equal to 2, so it could be considered as a theta 2. So this equation 2 will be cancelled. The final equation remain with us is theta I is simply pi multiply with I minus 1, where I is an integer which can vary, which can take only two value in this binary phase shift key. Either it may be 1 or 2. So first we place I is equal to 1 in this equation. So we are getting theta I is equal to 1 minus 1, 0. So we have a 0 phase. And if we place I is equal to 2 here, so that is 2 minus 1 pi. So here the symbol, two symbol in binary phase shift key can be represented with the two different phase. It is 0 and pi. So if we can say the binary phase shift key has a two symbols. So first symbol is simply S1, then S1 can have a phase of 0 degree. The another symbol S2 can have a phase of a pi. So if you place this value theta I in the equation number 1, so this equation, earlier equation can be modified as y BPSK of t is equal to square root 2 EB by TB into cos omega ct plus theta I, where I is equal to 1 here, which is correspondence with the input x of t is equal to 1. So theta I is equal to 0 in this case, and if you put here in the equation number 1, so that would be a 0. So we have the equation the equation of square root 2 EB by TB cos omega ct only. So that is written over here. If you take I is equal to 2 here, so for I is equal to 2, what happened? This equation need to modify. So that is I is equal to 2. If you put here, this is for I is equal to 1, and this is correspondence with I is equal to 2. So we are getting theta I is equal to pi. So this equation is square root 2 EB by TB cos omega ct plus pi. This is omega ct plus pi, and it is equivalent to minus, this is here, we can say it's a cos omega ct plus pi, because theta 1 is pi here. This is theta 1, and which is pi, which is written over here. And what is cos omega ct plus pi? It is minus cos omega ct. So the first symbol, if x of t would be a 1, we will transmit the BPSK modulator signal as a square root 2 EB by TB cos omega ct. And if we have input x of t would be a 0, so we can transmit the signal as a minus square root 2 EB by TB cos omega ct. So this is a positive sign here, and this is positive sign here and this one is a negative sign here. So it indicates there would be a 180 degree phase shift between two symbols. And this 180 degree phase shift is correspondence with the pi degree phase shift, which is shown over here. Pi degree phase shift. Now we will see the graphical illustration of the signal. So we can conclude here from this equation, if the input bit would be a 1, we will transmit the square root 2b by tb cos omega ct. So that is correspondence with the theta is 0 degree. And if we have x of t is equal to 0, we can transmit the signal with minus square root 2b by tb cos omega ct, and that is correspondence with the pi degree phase shift. So there would be a pi degree phase shift difference between the two signal, between two symbols. So let's assume x of t signal would be a binary signal, maybe in form of a 101101. And here we assume, rather than the earlier case, we are defining 1 with the positive pulse and 0 with the negative pulse, right? 1 with the positive pulse and 0 with the negative amplitude. You can say it is -1 and it is +1 here. It is multiplied with the carrier signal. So when there would be a 1, we have a 0 degree phase shift. So cos, the same cos would be copy here. You can see the same cos is copy here. Now when there would be a 0 in this second case, so this is the clock signal. So what we can observe here is there would be, sorry, I would like to take some another color. So you can observe here, there would be another carrier signal with 180 degree phase shift. So this one is correspondence with the 180 degree phase shift. Now again there would be a 1, there would be again 1, so here again there would be a 180 degree phase shift. So we can see here there is again 180 degree phase shift, right? Here there is a transition from 1 to 1. So 1 to 1 means there will be no phase change, because this one already has a pi degree phase shift. This will be continue with the next one. There would be again 0, so it is again here. At this point you can say we have again phase shift. There would be again 0 to 1, so again there would be a phase shift. There is a phase shift here, so there would be again a phase shift. So we can say when there would be 0 bit and the next bit, this is the present bit, and if the next bit would be a 1, so in that case we have a pi degree phase shift. The similar happens if your present bit would be a 1 and the next bit would be a 0, there would be again minus pi degree or maybe a pi degree phase shift, right? If you have a 1 to 1 transition, there would be a no 0 degree phase shift. If there would be a 0 to 0 transition, there would be a 0 degree phase shift. So whenever the bit is going to change, if the symbol S1 retain, we do not have a phase shift is observed. Whenever S2 is retained in the next bit also, there would be again no phase shift. But if there would be a transition from symbol S1 to symbol S2 or symbol S2 to symbol S1, so we have a pi degree phase shift is observed. So that can be noted down. Okay, so now here we can say BPSK is less susceptible to the noise. So if the noise are added, so it may not be affect too much. The BPSK is less susceptible to noise as compared to the earlier case of amplitude shift key, because here the information are stored in a phase, not in form of a amplitude. So noise is basically affect the amplitude more compared to the phase. So if informations are stored in a form of a phase, then the noise is less affected. And what the receiver have to do? Receiver have to identify the correct phase to recover the original signal back from the BPSK modulated signal. So effect of noise is less, and that is the main advantage part, and that's why it is a key technology. When we learn QPSK, so QPSK will be a key technology of the CDMA, and this QPSK belongs to the phase shift key PSK family. Now we will learn the constellation diagram of this. So for a constellation diagram, we represent both the symbol S1 and S2 with its amplitude and phase. So we can say generally amplitude, the relation between amplitude and energy is that the amplitude square is equal to energy of the symbol. And if you define the energy of the symbol, E is a ES, so that is simply defined as energy per symbol. And here one symbol is equal to 1 bit, so energy per symbol is equal to energy per bit, we can say. But this is not the case if you move further for MRE PSK signal, QPSK signal, 8 PSK signal, etc. But at this point it is reasonable to assume ES may be equal to EB because the bit and symbol are identical here. Bit rate and symbol rate are also equal. So if RS is the symbol rate and bit rate is also equal, and the energy per symbol is also equal to the energy per bit. So if you learn the constellation diagram, so the constellation diagram is amplitude square is equal to energy of a symbol. Energy is basically the amplitude square here because we represent everything by the pulses. So pulses has some amplitude, and if you take the amplitude square or symbol, pulse may either maybe in pulse or symbol. So symbol has some amplitude, and if you take the amplitude square, then we are getting the energy. So amplitude, if you define this equation in form of amplitude, so it's a square root of energy. And if energy per symbol is simply defined by the ES, so energy of symbol is simply defined by ES, so amplitude is simple square root of ES. So what we have marked here is, if you have a bit 1, we can transmit with cos omega ct with the 0 degree phase shift, and if we have a bit 0, we can transmit with the pi degree phase shift. It's a minus square root 2 EB by TB cos omega ct. So if the energy will be considered, so first one has a positive energy, so that is written here. So first one is a positive energy, is simply known as a ES. And if you draw the constellation diagram with a real axis, on x axis is a real axis and y axis here is the imaginary axis. So we can find we have a 2 energy for symbol 1. So if there would be S1, so S1 has this energy which is simple defined by ES1, and energy of symbol 2 can be defined with the ES2. But in a phase shift key, the informations are stored in form of a phase, not in form of a amplitude. So we can say if the amplitudes are equal for both the symbol S1 and S2, so energy is also identical. Energy may not be changed because energy is not depends on frequency and phase. Energy depends on amplitude, and in phase shift key here we have observed the amplitude of your signal A and minus A is not going to change. That remains a constant. Unlike ASK, in ASK signal the difference is observed in amplitude, but in PSK signal the difference is in form of a phase, not in form of a amplitude. So both the symbols have the same amplitude, only they are differ in terms of a phase. So if they have the same amplitude, their energy are also equal. So we can say the energy of ES1, the symbol 1 energy, is equal to the energy of symbol 2, and that can be simple written as the energy of symbol as ES, because both have the same energy. So we can denote as a ES is energy per symbol. So here we can represent the symbol 1 S1 away defined by the positive phase, so its energy is the square root ES. The second symbol here, sorry, I have to write its absolute value here, so that may be better to understand, is equal to absolute value of symbol 2 energy is equal to this we can say absolute value of ES, right? So the energy per symbol is simply defined by a square root ES. That is, now we can have to say if you remove this absolute value, that is a ES, right? and energy per second symbol is minus sorry, amplitude energy is always positive, so we can say the amplitude, this is the amplitude of a first symbol. S1 symbol has the amplitude of a square root es, and the S2 symbol here have an amplitude of a minus square root es. So these are the amplitude of symbol 1 S1. And what is this? So this is the amplitude of symbol 2s2. So and if you find the distance between these 2 points S1 and S2, so this distance is minimum here, and this minimum distance which is directly line of sight distance, and this distance is square root 2es. And where we can put the threshold here when if signal is corrupted by the noise. So we are using a threshold detection, and so for threshold detection mechanisms we will compare with the threshold value. If something is above threshold, we will take the decision in favor of S1 symbol. If something is below the threshold, we will take the decision in favor of symbol S2. So threshold can be put as a midpoint which is at 0. So this can be understood. This is a constellation diagram. In constellation diagram, we are getting a 2 points, 2 different amplitude. One amplitude is a positive amplitude which represents the symbol S1 because it is correspondence with a 0 degree phase shift. The another which is correspondence with the pi degree phase shift. This is S2 symbol, and this S2 symbol can be defined by negative sign because of this negative sign indicate the pi degree phase shift. So that can be defined by the minus square root es. Okay, so this is the es is the symbol energy. Here one symbol is equal to 1 bit, symbol energy is equal to bit energy. So these two are equal, that we have already discussed earlier. Now we come to the next point, is the bandwidth efficiency. So bandwidth is basically depends on how many frequency component lies in the signal. If we have a signal in a time domain represent as a y BPSK of t, we take the Fourier transform of this. So this one is not a frequency, this is simply represented as a Fourier transform. So if you take here the Fourier transform here, it's known as a ft. We are getting the signal in frequency domain as a y BPSK of f. And if you find here the power spectral density, if you find the power spectral density, it's Sy of f. And if you plot the graph of power spectral density Sy f versus the frequency f, so we are getting this portion, and in this portion the middle frequency is fc, and the bandwidth of the signal is simply defined by b. So that shows the bandwidth of a PSK signal is a minimum, which is B or RB, which is similar or equal to the bandwidth of ASK signal. So ASK signal and BPSK signal have a same benefit, but what is the advantage of BPSK signal? It is less susceptible to the noise compared to the ASK signal. So it's a bandwidth efficient scheme because the minimum bandwidth required is B. We have only one carrier, and the reason is the BPSK signal has a single carrier is used. Only single carrier cos omega ct is used here. Yeah, they are different in terms of a phase, not in terms of a frequency, but they are different in terms of a phase, and phase is not basically the parameters which affect the bandwidth. The bandwidth is affected mostly by the frequency component. So only single frequency components is present in our signal, and that's why this bandwidth is concentrated with that frequency fc, and which is the minimum, and this minimum bandwidth is defined by rb. So that is a BPSK is considered as a bandwidth efficient scheme. However, if you discuss about FSK, frequency shift key, so it is not a bandwidth efficient scheme because in FSK we require a 2 RB, which is double the bandwidth of amplitude shift key and a phase shift key. So FSK is not a bandwidth efficient scheme, but ASK and BPS, binary ASK and binary PSK is a bandwidth efficient scheme. So this point you need to note down. Now we discuss about the BPSK transmitter. So in this diagram, the BPSK transmitter is simply the bit 1 and 0 is to be converted in this bit basically, this is a on-off signal, and this bit are basically converted to the polar signal. So in a polar signal, we will define the 1, this is 1, which is represented as a 1, the 0 is represented as a -1, this 1 is again represented as a 1, and 0 is represented as a -1. So we are converting 1 to 1 here and 0 to -1 here. So these two things you need to run down, and this is the case of a bipolar. So that's why we have a basically this is a polar signal. Bipolar we are using for a different context. So this is a polar signal. We will convert on-off signal, every on-off signal, to polar signal in a first step. So this is the step number 1. Why we are converting this on-off signal to polar signal? So there is a specific reason. If we are converting in a polar signal, so we directly multiply the signal with the carrier signal. So this is the carrier signal, which is simple cos omega ct. So what happens here? You can observe, if the input bit, right, input bit would be a 1, right? So this 1 would be multiplied with the cos omega ct. This is multiply here, and this is a multiplier. Balance modulator work as a multiplier. So this is 1 which work as a multiplier. And after multiplication, if there would be a bit 1, and it is multiplied with the carrier signal, so what you are getting here, if this is my y BPSK signal, so this signal is simply defined as the cos omega ct. So that is multiply here, and then finally you are getting here as, if bit is 1, then if bit is here, the input of balance modulator is b of t. If b of t would be a 1, then your output of BPSK would be a cos omega ct. And if your bit would be a -1, then your output would be a minus cos omega ct. I have skipped this portion of square root EB by TB over here for simplicity purpose, that you can understand. So, but so if your input here is 1, if input is 1, we are producing cos omega ct. If your input would be a -1, we are producing minus cos omega ct here. But this 1 is basically a 0. If you are considering this is our x of t is an input, so x of t would be a 0, and passing through this a polar level encoder, it will be converted to -1. So it means simply 0, this minus cos omega ct is simply correspondence with 0. And if your input x of t would be a 1, that is remains same after passing through the NRZ level encoder, and that is cos omega ct. So it means 1 is directly correspondence with cos omega ct. And this one is very much similar what we have discussed here. If x of t would be a 1, then we have a cos omega ct. If x of t would be a 0, we have a cos omega ct, but with the negative sign. So that one we can understood. So this is a similar thing, and here for this similar thing, we can conclude this BPSK transmitter is very simple block. In the BPSK transmitter, the first, whatever the data are available with us in terms of a 1 and 0, we are converting to the polar signal 1 and -1, that is fed to the balance modulator. The balance modulator is simply multiplied with cos omega ct, and then finally the BPSK signal can be produced here. Okay, so this is one part. Now we discuss the BPSK receiver, and again the receiver can be classified in 2 categories, in synchronous and asynchronous, or we can say coherence and non-coherence. But this BPSK receiver, it is very popular. It is known as a found by the scientist Costa, so it is known as a Costa's loop. Here we are using the same principle of a phase lock loop. What happens in a phase lock loop here? I again refresh your memory. So in a phase lock loop is simple. You have an input signal. Let's say your input signal would be a x of t, which is given here. Then you have a feedback signal, which is simply known as x dash of t. And if the input signal is represent with some signal a cos theta I 0 of t, and if your x dash of t is represented as b cos theta I of t, we will take the difference here. So this is positive, this is negative. So we will simply multiply here, not difference. If you simply multiply here, then we are getting the two signal AB cos theta I plus theta 0 of t, theta I minus theta 0 of t, and it should be passed, this both the components should be passed through the low pass filter. So low pass filter will allow to pass only one signal which is of a lower frequency. So if here we can have a two signal cos theta I plus theta 0 and cos theta I minus theta 0. This one will be blocked because it should be considered as a high frequency signal. Only this one can pass. So at the output we are getting here the signal only cos theta I minus theta 0 of t. It is given, this one is given to the voltage control oscillator. So voltage control oscillator will convert the DC value of the signal to the another frequency component. We are here getting cos theta I of t, new value of theta I of t. So this one is known as a loop filter. This is the voltage control oscillator. The input is the DC signal, and correspondence to DC signal difference. The DC signal is basically difference between these two signal incoming and whatever the locally generated. So this is the incoming signal, and this is the locally generated signal. And the main objective is to match these two frequency. If the theta 0 is larger than theta I, so the difference here generated will be such that the next time the frequency of the output of VCO output will be increased. So VCO is basically convert your DC signal in correspondence to the frequency difference. So if DC signal would be a positive, then next time we are generating F2 frequency which is larger than the previous frequency F1. And if the DC signal is a negative, the next time we are generating F2 frequency would be a smaller than F1 frequency, and try to match this both the frequency. Whenever theta I and theta 2 would be matched, then this frequency is to be log. So this is a very important part, and this is the same thing we are trying to apply over here. Basically there are some difference over here. We have considered cos omega ct earlier, so our signal is basically cos omega ct, but here in this diagram they use the sine omega it. But let's assume there would be no difference if we change from cos to sine. And m of t signal is the original signal, so m of t is like your x of t signal. It can take the two value, either 1 or maybe a minus 1 or maybe a 0, right? Maybe a minus 1 you can say. So your signal is received as either sine omega ct plus theta I or maybe minus sine omega ct plus theta I. The sine and cos have no difference. Earlier we have considered cosine, but in this diagram it's shown as sine, but this is the same thing. So now this both will be parallelly in this Costas loop, both are parallelly applied to lower branch and upper branch. The upper branch is simply known as a Q arm signal, lower branch is simply known as I arm signal. Whatever the signal is present here, this one is the similar what we have discussed earlier. So this is our VCO. This is similar to our VCO, voltage control oscilloscope. This is the VCO. This is the loop filter. This is simply known as a loop filter, will allow to pass only one component and block the second component. This is also a loop filter for a lower branch. This work as a VCO. So what happens here? So we can start from here initially, right? So let's say we can start from here. So this VCO will generate the 2 cos omega it plus theta 0, which will be multiplied here. This is the similar multiplier what we have discussed here. Multiply with the incoming signal. sine omega it plus theta I. So you are getting the two components sine into cos. So we are getting here the two component sine theta I minus theta 0 into omega it theta I plus theta 0. This one is of a low frequency signal and this one is high frequency signal, because this omega I is nothing else but it is omega c, so which is centralized to somewhere at carrier frequency plus this, and it is simply theta I minus theta 0. So this is low frequency signal. So here we are getting both the components. This is y0 output, this is incoming signal, this is locally generated signal. So this one is correspondence to this one and this one is similar of this one. Both are multiply, we getting the two components. One component which is passed through this loop filter is the low frequency component. So this one is a low frequency component, m of t sine theta minus theta 0, it will be passed. This is finally available here. Similar expression can be represented for I arm. So for I arm, let's define it's my output is y1 dash, y1 is the output after multiplication. So if you multiply with the minus sign and then if you do the similar process for a lower branch also and then pass through the loop filter, so finally in the output of a loop filter we are getting m of t cos theta I minus theta 0. Theta is the incoming signal and theta 0 is locally generated signal, which is the deeper than this one, so we can consider it's a theta I and theta 0. So you understand like that. So finally the two signals are available at the output of the low pass filter for upper branch and low pass filter for a lower branch, that is m of t sine theta I minus theta 0 for upper branch and m of t cos theta I minus theta 0 for lower branch. Both will be multiplied, then they will be produce a 1/2 sine 2 theta I, and that would be recurring, where theta I is equal to theta E is equal to theta I minus theta 0. This one theta E is equal to theta I, it's a difference. So this one goes inside, then again given to the voltage control oscillator and produce a cosine signal. After pi/2 phase shift, it becomes a sine. It is multiplied with incoming signal. This is also multiplied in incoming signal. Then two components are produced here, two components are produced here, pass through the low pass filter. It allowed to pass only one component, it also allowed to pass only one component. So output of a upper branch is m of t sine theta I minus theta 0, output of lower branch is m of t cos theta I minus theta 0. And here we are getting output. How? So whenever the theta I is equal to, after this iterative process, what we basically do, we don't know the phase of incoming signal. So here by this phase lock loop, we try to generate the locally the phase theta 0, and this is a negative feedback. So if theta 0 would be greater than the theta I, so next time the frequency or phase would be decreased, and theta 0 would be less than the theta I, then the next time the phase will be increased. And at one point when our locally generated phase theta I can exactly match with the incoming phase theta 0, and when this happens, then this becomes a 1, because this both are equal. So a cos 0 degree would be 1, and when this would be 1, we are getting our original signal back m of t. So if m of t would be 1, we are getting m of t would be 1. If m of t would be minus 1, then we are getting m of t would be minus 1. So here this is the looping mechanism. So what we conclude here, if the phase is correctly identified at the receiver, then the information can be retrieved correctly. Means m of t information is what? M of t. So m of t will be correctly retrieved. Okay, so this is the thing, and what we basically learn here, if your incoming signal theta I greater than theta 0, so what happens next time? Theta I should be decrease. Theta I should be decreased, and if we are getting theta I is less than theta 0, then we need to increase the theta I. So if theta I greater than theta 0, the difference here is the DC signal, which is of a positive. what is there, theta I minus theta 0. So sorry, yeah, theta I is the incoming signal, so which is larger than theta. Then theta I should be theta 0 in our control, not theta I. So theta 0 would be increase because it is less, and which is the DC signal is positive, which trigger the VCO to generate the larger phase. And if the theta I is already less than theta 0, means incoming phase is smaller than the locally generated phase. So theta 0 should be tried to decrease, so it can be track the theta I. So DC signal which generate is as a negative, which trigger the VCO to decrease the theta 0. So that way we try to capture, and once we capture, then it will be log and we are getting a MOPT signal back. So this is the case that we have to learn. So in next lecture we will see the QPSK signal and REQAM signal, is known as a quadrature amplitude modulation. So till the date we will stop here and we will meet in the next lecture.